30. Okay, so let's start. Okay, good morning, good afternoon, and good evening. So, welcome to the last session of this workshop. And in this oral session, we have three speakers, three talks from the three experts in the area of dexterous manipulation. And before that, I want to give a kind of reminder to our audience. You can type in your questions during the presentation of the speaker, so that after they finish their presentation, they can see, everyone can see the question directly, so that we can ask and the speaker give us the answer. All right. So our first speaker will be Professor Janet Bohg from Stanford University. So Janet, could you please share the screen? In the meantime, I will give a short presentation introduction to Professor Bohg. So Professor Bohg is an assistant professor of computer science and at Stanford University. She was a group leader at the Autonomous Motion Department, in short AMD, of the MPI for Intelligent Systems until September 2017. Before joining AMD in January 2012, Professor Bohg was a PhD student at the Division of Robotics, Perception and Learning at KTH in Stockholm. In her thesis, she proposed novel methods towards multimodal scene understanding for robotic grasping. She also studied at Chalmers in Gothenburg and at the Technical University in Dresden, where she received her master in art and technology and her diploma in computer science, respectively. Her research focuses on perception and learning for autonomous robotic manipulation and grasping. She is specifically interested in developing methods that are goal-directed, real-time, and multimodal, such that they can provide meaningful feedback for execution and learning. Professor Bohg has received several early career and best paper awards, most notably the 2019 IEEE Robotics and Automation Society Early Career Award and the 2020 Robotics Science and System Earlier Career Award. So, Prof. Bohg, we are ready.
Thank you very much for the kind introduction and for the invitation to speak at this workshop. So I looked at the workshop description, and there was quite some emphasis on how to imitate humans for context-rich tasks. So today I thought I'm going to talk a little bit about more on our work on how to leverage video demonstrations from people that can be scaled up quite well to have a robot learn a bunch of sensory motor skills. I think I was muted. Can you hear me?
Yes, yes.
Okay, sorry. It just, okay, perfect. Yeah, I don't know. Somehow I was automatically muted. I hope that's okay.
Yeah, I will remind you.
Thank you. All right, so recently, of course, there has been a lot of progress on robust low-level sensory motor skills. And here, just like two examples from my work, but of course, there's lots of other work around there. So this is a particular work that we've done a few years ago, where this robot Apollo had to grasp this Pringles box with the chips. And specifically, it had to avoid in real time all of these different obstacles that are keep appearing on the desk, and it has to do so within milliseconds. And here's an example, a different example from my lab, where we fused the modalities of vision and touch to allow a robot to learn like these kind of context-rich manipulation tasks like peg insertion, even if it may not know exactly the shape. And also my student Michelle here is actually perturbing it or perturbing the robot. It can still succeed. So, so these are different ways, or these two works, they show basically different ways on how to enable robot to do different manipulation skills. But it's really difficult to scale up the number of different skills and to do it in that way. So for example, on the right side, we used model-free reinforcement learning, which is of course great because the robot can learn by itself through try and error to do these tasks, but it can also take a lot of time to learn the skill. So learning from demonstration is really a great way for both humans and robots to bootstrap that kind of learning, even if it is through trial and error. But of course, in robotics, this is often, there are also many different ways on how to do learning from demonstration. So for example, there has been a lot of work, so I just picked one here that uses kinesthetic teaching to demonstrate a robot skill, and where basically a person physically moves the robot and demonstrates it in this way. And there are other works that actually use teleoperation. So here, for example, is a work called Roboturk that uses an actual phone to remotely teleoperate robots and demonstrate tasks. So these are all ways to enable learning from demonstration on a robot, but they can still be kind of tedious for a person to do, especially if they're non-experts. So we were wondering, wouldn't it be great if a robot could just imitate people by watching? Because if a robot could watch videos, we could potentially scale up the number of different tasks that a robot can do to many different contexts and to much more data as well. So scaling is somewhat easy if a robot could just watch, for example, YouTube videos. But of course, the big challenge with watching videos as opposed to using teleoperation or kinesthetic teaching as another way to provide demonstration is that there's no robot state really contained in this video. Sometimes it's even given by a person. You don't know where the end effectors is or what is actually important to imitate here. So this is the challenge we have been looking at, and I want to talk today about. I was planning to do 3 example projects, but I'm thinking maybe it will only be 2. So let's see how this goes. So I want to talk about 3 projects where we looked at this challenge of robots learning from videos. First, I want to talk about how a robot can learn from natural language instructions and human demonstrations. And then I want to talk about some very recent work where we also looked at specifically periodic tasks and how a robot can imitate this from single human demonstration and can directly imitate it through a few trials on a real robot. And we also looked at how we can use video demonstration to actually ground predicates and then enable closed loop task planning that potentially chain together different sensory motor skills. So let's see if we get to the last work. I think I can definitely cover the first 2. So let's start with the first one. And so in this part of the talk, in this first project, our goal was to endow, let me just move this for 1 second. We wanted to endow a robot with the ability to acquire something we call manipulation concepts. And these manipulation concepts can be seen as mental representation of verbs in a sentence. And given initial scene images, when we send various instructions, such as put something behind something or put something into something, we want our robot to generate motion trajectories that accomplish these tasks. And so to achieve this goal, we formulated this by constructing an embedding space that associates task instructions and scene images with motion trajectories. So constructing an embedding space of manipulation concepts offers several benefits. First, we can specify the manipulation task with language instructions instead of goal images, which is often done in related work. And describing the task with language is much simpler than providing a goal image. And second, we can obtain a multitask policy to represent diverse manipulation skills, such as open something and close something. And third, by training on a diverse set of manipulation tasks, our policy can generalize to novel but similar instructions. So how do we train the robot to output trajectories to accomplish tasks? So our approach, as you guessed from the title of the presentation, is to learn from visual demonstrations. And it allows us to avoid reward engineering or kinesthetic teaching or teleoperation, which are time consuming and difficult to scale up to a large number of different tasks. And so we use the 20 billion something something data set as the visual demonstrations. It contains around 200K video clips with 174 different action classes. And each video clip is annotated with a task description, such as putting something on a surface or moving something up. So, however, of course, there's a very large domain gap between the human demonstrations and robot simulation. So take close something as an example. In the left, you see 4 examples of closing something, but they're all quite different from the robot simulation. And so we really need a learning from visual demonstration method that can handle different backgrounds, different viewpoints, different objects, and so on. And so we address this large domain gap by using a video activity classifier to evaluate robot trajectories. So the video action classifier is firstly trained to classify the action label of each video clip in the 20 billion something something data set. And then we use this learned classifier to score robot videos. And the score represents how confident the video classifier estimates the robot video to belong to the corresponding activity. So the learning from demonstration pipeline works as follows. So first, we send language instructions and an initial scene image as the input to our model by concatenating their feature to provide semantic context. And you can see that we use pre-trained models here, like BERT for the language encoding and ResNet for the encoding of the image. And then a policy generation network outputs a motion trajectory specified as a goalpost and a series of forces to perturb the otherwise straight line trajectory. And next, this entire motion trajectory is executed open loop in simulation in this case, and we render it to get a video. And this video is sent to the activity classifier to get a score, which is used as a reward. And then we run a reinforcement learning algorithm to update the parameters of the motion trajectory to maximize the reward. So that's the overview of the method. And so, as I mentioned before, we use the 20 billion something something data set that contains 174 different action classes. And we selected 78 of these tasks, which are suitable for robot simulation. And we set up simulation environments and PyBullet, as you see here. And for each task, we train a policy using this learning from demonstration pipeline that I just showed you. So here are some examples of the 78 different tasks, and this is the task of closing something. So note that this is testing the policy with randomly generated initial object poses, in this case of a drawer. And here's another example that is called tilt something with something on it so that it falls. And again, you see there are different kind of states that are actually being executed here. So now we have 78 single task expert policies, each of which outputs motion trajectories to accomplish one specific task, like the one here. But remember, our ultimate goal was to construct a unified model to represent a diverse set of manipulation skills. And we formulate this as a multitask learning problem. We train the multitask policy by running behavior cloning on the previously learned single task expert trajectories. because with the single task expert, we now have actually access to the robot state as opposed to the videos that the robot was imitating. So that's why we can run behavior cloning. And the result is a unified model that can take in various instructions and scene images as input and output trajectories for these 78 different tasks, so with one policy. So here are some examples of this one policy that can execute 78 different tasks. You see these are quite diverse tasks. Some of them you have already seen, just with the difference now it's like one policy only. Here's some more that are actually quite complex as well. And we also could show that if we qualitatively, at least, if we alter the language instructions slightly and use these as input instead of the ones that the policy was trained on, we can still get reasonable behavior that does something that we asked the robot to do. Okay, so this work, if you're interested to read about all the details, is called Concept of Robot and was published at RSS in 2020. And the main idea is to learn an embedding space for manipulation concepts indexed by natural language instructions. And the algorithmic contribution is an imitation learning framework that can learn from human video demonstration where an activity classifier is used to provide the reward. And the result is this multitask policy that can execute 78 different tasks indexed by natural language instructions. Okay, so this is the first work. And I just want to go back into look again at the model that we used here and look again more closely at this architecture. So you see we used like language instructions here as input in the scene image to ask the robot to do a particular task. And then what is maybe somewhat different from what other works have used typically in learning from human demonstration is that we do not actually use a feedback policy. What we learn instead is a trajectory generator. You could think of it, if you're familiar with dynamic movement primitives, it's a variant of this. And it describes an entire motion, not just what to do in a particular state. And we found that this is much easier to learn than a feedback policy. And we can also see that it really captures what the essence of the particular action that may require an entire trajectory and an entire orientation as well. And then again, the classification of the video or the classifier here really looks at the entire video that the robot generates by executing this motion trajectory. And what this allows us to do is really to bridge this domain gap that I showed you before. And it also allows us to do or to take into account a great variety of demonstration context from many different videos. But what we also found that it is actually not that transparent on what is actually rewarded in the robot. And we also found that although we use this trajectory generator here in the middle to generate an entire trajectory instead of using a feedback policy, the training of these multitask policies still requires a lot of sample to learn using the specific proxy rewards. And so we could really only run this in simulation, although we use real videos of people to imitate. So in the next project that I'm going to show you, we actually wanted to look at a different kind of manipulation task, so specifically periodic tasks. And we wanted to see if we can also imitate human videos by using a policy representation or a trajectory generator instead of a feedback policy, and really imitate human video demonstration that are again much easier to demonstrate. So we wanted to really achieve the following things. First, we wanted to learn periodic tasks because they're actually really ubiquitous in our daily life. So these are tasks that you do over and over and over again until you reach a particular state that you want to achieve, right? And so you just want to keep repeating it. And typically these periodic tasks are actually executed with very difficult objects. So these can be these are often deformable objects or food or granular material, things like that, which are actually visually quite difficult to process. And so we wanted to have a robot learn to do these periodic tasks from human demonstration and from video demonstration specifically. And this is great because it can be scaled up, but it's also hard to do because you don't have robot states. And in this particular case, for these periodic tasks that you see here, you have these very difficult objects to actually manipulate. And of course, we want to do that also in very few trials on a real robot. So the question that we addressed in this work was, how can robots appropriately represent and learn periodic policies for manipulation tasks by watching humans? And yeah, so here's an overview of our method that is composed of two modules. So we have an unsupervised module that learns a model for key point correspondences between the motion of objects in the human demonstration and in robot trials. And then we have a parameter or a motion parameter optimization model that uses active learning. In this case, we use Bayesian optimization to adjust the parameters of a rhythmic dynamic motion primitive. So again, like in the work before, we used like a point-to-point variant of a dynamic motion primitive. Here you use a rhythmic formulation of this. And so to learn a visual representation that encodes object motion, regardless of which agent is actually manipulating it, we use an unsupervised key point learning technique called transporter to learn key point representation. And for learning this, we use 10 minutes of human play data, so of just like moving this object around, and 10 minutes of robot play data as input. And this data is actually unpaired. So they don't necessarily have to correspond to each other. So the learned key point representation can then be used as a distance function between the human demo and a given robot execution. And to learn the desired motion from this human demonstration within 50 trials on a real robot, we use Bayesian optimization, or BO, to search for parameters of a rhythmic DMP. So concretely, BO samples several single period waypoints in every trial. And the waypoints are interpolated, smoothed, and executed using a rhythmic DMP. And then the execution is labeled using the key point-based distance function to generate a similarity score. And this score is then used to update Bayesian optimization to get the next sample. So here's an example how this looks like. So as we run more trials, Bayesian optimization finds better and better rhythmic dynamic movement primitives that produce executions that visually resemble the human demonstration. And here's some results that we first of all have done in simulation. So these results show that our method can successfully imitate object motion in human demos in wiping, winding, and stirring tasks, which is what we evaluated in this work. And so here in this particular simulation work, we use a floating suction gripper in all of these three tasks. So there's no, you see this white dot there at the bottom, there's no robot attached to it. Okay, so, and then our real robot consists of a Kinova Gen 3 robot arm, an Intel Resonance camera, a table workspace, and an object to be manipulated. And we observed that the robot can also learn all three periodic tasks, and the robot execution is shown on the left, while the human demo and detected key points are shown on the right. So we first showed the wiping. This is where we show a winding of a cable, where we, oh, sorry, this is a little fast somehow, it's playing automatically. But so these are kind of the demonstrations of these three tasks. And you see that the key points are actually staying quite stable. And our learn skill can also be executed with different objects, repetition counts, and scale, which is the interesting part of actually encoding these tasks with periodic representation, such as a rhythmic DMP. So here, this was an execution of a learned stirring skill on a similar task with smaller, stirring thing. Okay, so just to summarize this part of the work, it's called Learning Periodic Tasks from Human Demonstration, and it was submitted to ICRA next year. And so the main idea is really to model periodic manipulation tasks by encoding periodicity in the policy representation, and thereby to allow easier learning of these kinds of sensory motor skills. And the algorithmic contribution was a framework to represent, learn, and execute these periodic tasks from video demonstration using key point correspondences and active learning through Bayesian optimization. And the result was that we could learn 3 periodic tasks with complex, deformable, or granular objects or materials on a real robot from a single human video demonstration in just a few trials. So let me check how I'm doing time-wise. I think I have like 4 minutes left according to my clock. So I will maybe talk a little bit about the last project as well, where we looked, where we went basically beyond sensory motor skills. And we wanted to look at whether we can use video demonstrations also to enable closed loop task planning, where you have to actually chain together these kinds of sensory motor skills that we learned in the first 2 projects. So here's how a robot is actually chaining together sensory motor skills and then executing a long horizon plan. And you see that student Toki here is actually perturbing the environment. So the robot has to recognize like, oh, I cannot actually continue with that particular task. I actually have to go and correct and maybe replan. And so this particular work that I'm going to talk about last is basically about how a robot can online figure out that it has to replan, essentially. So under the hood, we are basically using strips planning, which is very like just a search for a symbolic action plan based on pre and post conditions of discrete action primitives. So this kind of planning is well understood and works if you have a description of a planning domain, which we assume we have here. And you see that, outlined almost here. This is like for a different planning domain than for the video you just saw. So often deriving this planning domain is actually quite straightforward, and I will come back to that point later. But the outcome of this strips planning is basically a planning tree where you see the nodes represent the current state of the environment, an edge represents an action that changes the symbolic state in a predefined way. So we want to use this kind of symbolic task planner to provide a longer horizon high-level plan and trigger the correct low-level sensory motor skills. But now the tricky question really becomes, how do we perceive the symbolic state of the environment for the many possible predicates that are now required for planning over this large variety of actions? And besides grounding these abstract symbols, we also want to enable continuous task planning. So this part of the talk is basically about that. And I think I'm kind of actually running out of time. So let me maybe skip through these slides where I talk about how we model this. So we're basically, sorry, I cannot actually, let me see if I can actually skip forward. So maybe just to explain the main idea, we assume we have a planning domain and we have videos that are annotated with actions. And so, for example, we have an action like this, put an egg into a bowl. And we know that, that this kind of action from our planning domain is changing basically the state of the environment in a predefined way. So here for this particular example, right, the egg is in the hand first and not yet in the bowl. And after the action is executed, we know that the state has been changed in that way. And so this knowledge and the given images we can use to actually ground these symbols and then train a predicate classifier. And so I don't think I have time to actually go through this. in detail. So I will just maybe show you what we can actually do with that idea of using actions and videos to train classifiers. So here is an example of approaching something with your camera, and you can see that we can monitor this video and actually see how the different predicates change online and go from preconditions to post-conditions. And we have similarly other examples, like here, for example, with the book, or here breaking a toothpick, where you see that the states or the predicates are really changing in a meaningful way. Here's a different example that is all basically using predicate classifiers that are trained with that idea of using actions to label the state in not annotated videos. And so to come back to this example of how do we plug this in now into a robotic system. So again, the task here of the robot is to remove the fruit from the table. And so all the fruit have to basically be moved from the surface. And here you see the action skeleton that the task planner came up. And then on the bottom, you see the monitoring of the different predicates that are used to do the online replanning as well. Okay, so yeah, so this was the work that we just submitted to RAL, and it exploits that actions change the symbolic state in a known way for cheap proposition labeling of video demonstrations. And we provide this entire framework, and so we can learn these 37 predicate classifiers relevant to these 172 actions, and then we can use it for closed loop task planning. So with that, I end my talk. Thank you very much for your attention and for the invitation again. So I'm happy to answer any questions.